Now you may ask, how do we know where and when to draw the resonance structures? So there are a few patterns that you can recognize them in the molecules and based on them draw the resonance structures. We are going to discuss them together. I found them very useful to use while drawing resonance structures. But I can say the only way to recognize these patterns is to do lots of practice. All right. So you have a few practice problems available in ACE Organic. You also have access to your textbook. It has very nice practice problems, so you can work through them. And if you have any questions, as always, feel welcome to come to my office hour. We are going to discuss them together. The first pattern is allylic lone pair. So I don't want you to know the name of these patterns that we are going to talk about. What I want you to know is to be able to recognize them by looking at the molecules and be able to draw appropriate resonance structures. So first, what does allylic mean? When we have double bond, we are dealing with two positions. The first one is vinylic position. Atoms of the pi bond, we call them vinylic. And the next one is allylic positions. The next atoms next door to the double bond, we call them allylic. So that atom has a single bond after that and then double bond. So this position is allylic position. Now if you look at this molecule or the structure, better say, at the top, we have a double bond, single bond, and then lone pair of electrons. So this lone pair is allylic lone pair. And to draw the resonance structure, when you have allylic lone pair, you need to use two arrows. Okay. So the first arrow starts from the lone pair of electrons, move to the single bond to make a double bond. Let me draw the resonance sign here. Okay. And the next arrow goes from the double bond to make a lone pair of electrons. Okay, right here. Then we need to calculate the formal charge, and carbon gets -1 charge. So this is how we draw resonance structure while we have allylic lone pair. Now let's look at a couple of examples here. The first one is this example. Okay, so we have a double bond, single bond, and then lone pair of electrons on oxygen. So I want to mention that the lone pair can be on oxygen, on carbon, on nitrogen. What matters here is the position of the lone pairs here, which is allylic to this carbon-carbon double bond. So again, we start from the lone pair. Lone pair goes to make a double bond, and then the pi bond goes to make a lone pair of electrons. So we are gonna have, okay, I use one lone pair to make a double bond, so I still have this one on oxygen. I draw that. This is the double bond, and then I move the double bond to make lone pair of electrons. Then I need to calculate the formal charges, and the formal charge here on carbon, it would be -1, and on oxygen with 3 bonds and a lone pair of electrons, is +1 charge. Another example we can work on is this molecule. Okay. Now, so if you look at this one, we have carbon-nitrogen double bond. We don't have carbon-carbon double bond. So allylic position makes sense when you only have carbon-carbon double bond. However, for our purpose, if you look at this molecule, that's following the allylic lone pair pattern. So for our purpose, we don't care what do we have basically on a pi bond, whether it's carbon or nitrogen. What we care about is the position of these lone pairs, which is allylic to the double bond. So again, we start from the lone pair. We recognize our lone pair, which is right here. It moves to make a double bond, and then electrons in the pi bond move to make a lone pair. Okay, so that makes a double bond, and this one moves to make a lone pair of electrons. So see, I already have a lone pair here, so I should have 2 lone pairs on nitrogen then. All right, then I need to calculate formal charge, and by doing that, nitrogen gets -1 charge. So be very careful while drawing resonance structure. Always calculate the formal charges, especially for the basically atoms that are involved in the resonance. All right. Now we have a practice problem here. So find the allylic lone pairs in this molecule. And if you look at this molecule, we have a double bond here. So therefore, this lone pair of electrons is allylic to the double bond. That one is not. This one, it's just a lone pair. So non-allylic lone pair. This is the allylic lone pair. The second pattern is allylic carbocation. Again, we are focusing on allylic positions, but this time we are looking for a positive charge located in an allylic position. So we have our carbon-carbon double bond, and we have a positive charge on the allylic position. So to draw the resonance structure in this pattern, we are only using one arrow. Okay? And that arrow moves from the pi bond to make a new pi bond. Okay, so as you can see here, we have a pi bond that moves here to make a new pi bond, and then we need to calculate formal charges. This carbon gets +1 charge. So a good example here can be structure like this. Okay, we have a double bond and a positive charge in the allylic position. So we draw the resonance structure. So we move the pi bond to make a new pi bond. Okay, so I didn't touch this part of the molecule, so it stays the same. I draw the same thing. Now this double bond moved here. Let me number the carbons, so I think it would be easier to follow. Alright, so now the new bond is between carbon 1 and 2, and then carbon 3 gets the positive charge. Okay, then again I have this double bond and a plus charge, so again a new allylic position. I can draw another resonance structure here. So the pi bond moves here, over the carbon. Okay. So I didn't touch this part of the molecule, right? So I draw it as it is. Now in here, the double bond now moves to make a double bond between carbon 3 and 4. And then the carbon 5 lacks the electron, so it gets the plus charge. Okay, so these are all three resonance structures that we can draw for this molecule, and always after drawing the resonance structure, remember to put them in bracket. Okay, that shows these are different resonance structures of a single molecule. And when we have multiple pi bonds, multiple resonance structures are always possible. We have a definition here that I would like to mention, and that is the definition of conjugated system. So conjugated system is when we have more than one pi bond in the molecule, and those pi bonds are separated by one sigma bond from one another. So So be very careful of that one sigma bond, okay? So if you look at this system right here, we have a double bond, sigma bond, double bond. So this is a conjugated pi system. But if you look at this system right here, okay? So we have a double bond, sigma bond, double bond, sigma bond, sigma bond. So up to here, we have a conjugated pi system. But this one is not a part of conjugated system. So more than one pi bond separated by only one sigma bond gives us conjugated system. Sometimes we have a positive or negative charge conjugated with a pi system as well. So what does that mean? If you look at the first example that we worked on, right here, this pi conjugated system, okay, so we have a pi bond separated with a sigma bond with another pi bond, and then we have a charge which is also separated with a sigma bond with a pi bond. So we call that charge a conjugated positive charge because it is conjugated to the pi system. So in these situations, it is common that we combine all the arrows to each other to draw the last resonance structure. So I can push the pi bond here, push the second one here. Let me number the carbons to draw the last resonance structure. So I'm gonna have a new pi bond between carbon 1, 2, and a new pi bond between carbon 3 and 4, and now carbon 5 lacks the electron, so it becomes positive. Now if you compare this structure with this one, they are identical, but we combine the arrows to one another to get the last resonance structure. Now another example. Okay, so I have a lone pair which is allelic to the double bond, so I can follow the first pattern, which was basically using two arrows to push the charge. However, if you look at the whole pi system, I have a pi bond separated with a sigma bond with another pi bond, and then the lone pair is separated with this pi system with another sigma bond. So I can combine all the arrows to one another. Okay, I push the lone pair to make a new pi bond. This pi bond moves here, and this pi bond moves here to make a lone pair. Okay, so I have lone pair here, a double bond, and a double bond. Okay, so you can also draw all the resonance structures for this compound by pushing the arrows one by one, but it is also common, so you will see that we combine all the arrows to one another to get the last resonance structure. The third pattern is a lone pair adjacent to the carbocation or positively charged carbon. So here we have a lone pair of electrons adjacent to the carbocation. They are separated from one another with a sigma bond. Now to draw the resonance structure, we use one arrow, and the tail of the arrow starts from the lone pair to make a pi bond, between the carbocation and its neighboring atom. That has a lone pair. So if you look at here, the tail starts from the lone pair to make a double bond between the carbocation and the atom that had the lone pair. So to make a double bond between carbon and oxygen here. Now a good example here can be this structure. Okay. So we don't have any double bond here, right? So we cannot think of allelic positions. Now we have a lone pair, a single bond, and a positively charged carbon. So we can think of drawing the resonance structure by moving this lone pair here. Okay. So I only used one lone pair, so I should have the other one on oxygen right here. Now we need to calculate the formal charge. So the formal charge for carbon is 0, and oxygen, again, familiar pattern, oxygen with 3 bonds and a lone pair of electrons, always positively charged. Okay, so these are the resonance structures for this specific molecule. The fourth pattern is a pi bond between atoms of different electronegativity. So basically this pattern is the opposite of the third pattern. You saw this structure in the third pattern. So this is just the opposite. And we are focusing on the double bond between carbon oxygen and carbon nitrogen mainly. And to draw the resonance structure, we are using one arrow. Okay. And that arrow starts from the pi bond to make a lone pair on the more electronegative atom. Okay, so we never draw the arrow in the reverse order. All right, it is always from the pi bond to the more electronegative atom. So it's more electronegative, it likes the electrons more, and this is how we draw the resonance structures. And the fifth pattern is the conjugated pi bonds in a ring. So I already defined the conjugated pi bond for you, meaning that we have a double bond, single bond, double bond, single bond, but in a cyclic pattern. All right, and this structure specifically, it's benzene. Okay, so we can move the pi electrons in a ring and basically switch them in a ring to draw the next resonance structure for that. So this is the summary of 5 patterns that we just discussed together. So the first one is allylic lone pair. We are using 2 curved arrow here. Starts from the lone pair, form a double bond, and then double bond forms a lone pair. The next one was allylic carbocation. So in allylic carbocation, we only use 1 curved arrow from the lone pair, from the pi bond to make a new pi bond. Then we have lone pair adjacent to carbocation, so we are using that lone pair to make a pi bond with 1 curved arrow. The fourth one, we have double bond between 2 atoms with different electronegativity, and in this course we are focusing on carbon oxygen and carbon nitrogen. We are using 1 curved arrow to move the pi bond and make a lone pair. And the last one was conjugated pi system in a ring, and we are using 3 curved arrow. Now let's look at this practice problem and see what pattern we can recognize here. So if you look at this molecule, you can see the positively charged carbon. So you can think of either pattern 2 or 3. Since we only have double bond, therefore this is pattern 2. So this is allylic carbocation. And we can draw the resonance structure for that using 1 arrow from a pi bond to make a double bond. So be very careful. Only pi bond can move. Never put the tail on a single bond. Okay, single bond cannot move. Be very careful of that. So the resonance structure would be, I didn't touch this part of the molecule, and also this part. So I just move the pi bond here. Now this carbon gets positively charged. Again, if you look at this molecule, you can recognize the next allylic carbocation with this double bond. So you can move the pi bond here to draw the next resonance structure. I didn't touch this part, stay the same. This moves here and this carbon gets positive charge. And we put them in bracket. Alright. The next example could be this molecule. Okay. So if you look at this one, we need to recognize the pattern. So what I suggest you to do first, when you see that negative charge, make sure that you draw all the lone pairs so you don't miss them. Nitrogen, negatively charged nitrogen, always has 2 lone pairs. All right. Now, by looking at this, we have a double bond. So we can either think of allylic lone pair or allylic carbocation. And as you can see here, we have the lone pair of electrons, so it is allylic lone pair. And to draw the resonance structure, we know that we need to use 2 arrows. The first one starts from the lone pair to make a pi bond. And the next one starts from the pi bond to make a lone pair. So always draw the tail on a pi bond. Be very careful not to put it on a single bond. And okay, so this pi bond becomes lone pair on carbon, and we have double bond here. I use one of the lone pairs on nitrogen and CH3. Alright, now I need to calculate the formal charge. So the formal charge on nitrogen is 0. Now to calculate the formal charge on carbon, don't forget that I have hydrogen here. Okay, don't forget it. Okay, we didn't touch it. And the formal charge on the carbon would be -1. Okay, so this is the resonance structure for this molecule. A few practice problems here. The first one is asking to draw all resonance structures for the structure shown here. Before recognizing the patterns, what I suggest you to do is to draw all lone pairs of electrons on a molecule. That makes your life much easier while recognizing the patterns and drawing resonance structures. So I start with oxygen, divalent oxygen. I know that it has 2 lone pairs of electrons on it. So I draw them here. And then I have negatively charged carbon. I know that carbon, negatively charged, has a lone pair of electrons. Right? And I draw that here. Now we need to recognize the pattern. So I start with this lone pair. I have lone pair of electrons, single bond, double bond. So it's allylic lone pair. And to draw the resonance structure, I need to use 2 curved arrows. The first one start from the lone pair to make a double bond, and the other one from the pi bond to make a lone pair. Alright, so this is my lone pair, and I didn't touch this part of the molecule, so I draw that as it is. Now, again, I need to calculate the formal charges, especially on the atom that were involved in the resonance. So by doing that, this carbon gets the negative charge. Then if I look at this structure, again I can recognize allylic lone pair. So I have a lone pair of electrons here, single bond, double bond. So I can push the electrons and move them again. So using two curved arrows, make the new double bond, and then the pi bond forms lone pair. All right, this is my new double bond, and then so oxygen already had two lone pairs of electrons on it, and then new pair by moving by this arrow. Then I need to calculate the formal charges. So oxygen, monovalent oxygen with three lone pairs of electrons, it is always negatively charged. All right. And if you compare the formal charges, it's -1 in this structure, -1 here, and -1 here. So they are the same. And we can draw three resonance structures for this molecule. Now, the second practice problem is asking to draw the resonance structure indicated by the curved arrows. So if you compare these two structures, they are the same, right? All of them are the same. Both of them are the same. However, this bottom structure, it is showing all the curved arrows together. So let's draw the resonance structure for this electron movement. So the lone pair of electrons come here to make a double bond. Then the pi bond moves here to make a double bond. And then the pi bond moves on oxygen to make lone pair of electrons. Okay, and then calculate the formal charges. This is the structure that we get. So if you compare these two structures, they are the same. So therefore, sometimes you can merge arrows to get the last resonance structure. All right. Now the third practice problem is asking to draw all the curved arrows that shows the movement of electrons. To answer such a question, what you need to do, you need to compare both the structures, see where the electrons are and how they changed and how they moved in the molecule. So let's start with these two. Actually, let's number the atoms first. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I recognize that, okay, I have double bond, lone pair. So that could be my path to draw the resonance structure. Now, this oxygen has three lone pairs of electrons on it, but this oxygen, if I draw its lone pairs, has only two lone pairs of electrons on it. All right, so meaning that one lone pair here should actually moved to make a double bond here. All right, so that could show my first arrow. All right, then if I compare carbon 2 and 3, what I see, the double bond between carbon 2 and 3 is now between carbon 3 and 4. So the pi bond moved here. Then the double bond between carbon 4 and 5 now is between carbon 5 and 6. So the pi bond moved here, and then the double bond between carbon 6 and 7 converted to the lone pair of electrons. So the pi bond moves to form the lone pair. All right. This is how you can show the movement of electrons using the curved arrows in the first structure. Another important thing I would like to mention about this structure is you may ask why we don't push the electrons in the reverse pathway, meaning that why we don't start from here to push the pi bonds here and then this pi bond here. So if you focus right between the carbon 6 and 7, if I push the pi bond between carbon 5 and 6, what's happening is that carbon 7 lacks the electrons, so it should become positively charged. However, if you compare and look at this structure, carbon is negatively charged. This is how I recognize the pattern that, okay, if I go from oxygen and then move through this pathway, this carbon would get the negative charge.